Welcome to TalkTensors, the podcast where we dive deep into machine learning research.
Glad to be here.
Today we're looking at a really interesting paper. The title's a bit of a mouthful. Enhancing Deep Learning-Based Structured Illumination Microscopy Reconstruction with Light Field Awareness.
Right, quite descriptive. But you get straight to the point. It's all about using ML to push the boundaries of microscopy.
Exactly. How we see the really, really small stuff. Specifically in biology.
Yeah, so structured illumination microscopy, or SIM, is the technique in focus here. It's a smart way to beat the diffraction limit, that fundamental blurriness in microscopes.
So it lets us see finer details in, say, living cells.
Precisely. It uses patterned light, kind of like projecting stripes onto the sample, to extract higher resolution information than you'd normally get. It's become super important for live cell imaging.
But there's a catch, right, with traditional SIM?
There is. It really hinges on knowing exactly what those light patterns look like. Perfectly.
And in the real world, things aren't perfect.
Not at all. You get distortions, scattering from the sample itself, imperfections in the optics, all sorts of things. And that can lead to artifacts.
Artifacts meaning like visual glitches. Things that look real but aren't.
Exactly. Weird lines, extra fuzziness. It can really compromise the data, make you misinterpret what you're seeing.
Okay, so enter deep learning, DLSIM.
Right. Over the last few years, people realized neural networks could potentially clean this up. They can learn from data to reconstruct the images, often faster and, well, sometimes better than the old algorithms.
Handling some of that real-world messiness you mentioned.
Yeah, they could be more robust. There's been a lot of progress making them faster, need less light, which is good for the cells.
But there's always a but with ML, isn't there?
Often, yes. The big one here is the out-of-distribution problem.
The classic Achilles heel. The model sees something different than what it trained on.
Exactly. You train it on simulated data with maybe perfect or near perfect light patterns. Then you put it on a real microscope where the patterns are actually quite wonky.
And it struggles, produces its own kind of artifacts.
Precisely. The results can be inconsistent, unreliable, which isn't great for scientific discovery.
So this paper tackles that specific problem, the mismatch between training and reality.
That's the core contribution. They propose this new approach, awareness of light field SIM, ALSIM.
Awareness of light field. Okay, I like the name. What's the core idea?
Well, instead of just hoping the light field matches the training data or trying to pre-calibrate it perfectly, ALSIM actually tries to figure out what the light field really looks like during the experiment.
How does it do that?
It's a two-stage process. Stage one uses a neural network specifically trained to look at the raw SIM images.
The unprocessed data.
Yeah, the raw data coming off the camera. And from that, it predicts the actual light field patterns, distortions, and all.
Whoa, okay. So it's learning the imperfections from the experiment itself.
Kind of, yeah. It's estimating the physical reality of the illumination based on how the light interacted with the sample.
Okay, that's stage one. What about stage two?
Stage two is the reconstruction part. But here's the clever bit. They use the light fields predicted in stage one.
The ones with the real-world distortions?
Exactly. They use those predicted fields to generate new simulated training data for the second network. This simulated data now much more closely matches the actual experimental conditions.
Ah, I see. So the second network, the one doing the final image reconstruction, is trained on data that reflect the actual messiness because the first network figured that out.
You got it. It bridges that gap, that out-of-distribution problem, by making the training data distribution much closer to the test data distribution.
That sounds really elegant, actually.
It's a neat idea, and they tested it, of course, both on simulations where they knew the ground truth distortions, and on real microscope images, they used BSC1 cells, which are like a standard workhorse in cell biology labs.
And the results? Did it work?
It did, yeah. Visually, the images had noticeably fewer artifacts compared to standard DLSIM trained on idealized data.
Okay, fewer visual glitches. Did they quantify it?
They did. They measured the normalized root mean square error, NRMSE, and found ALSIM achieved about a 7% reduction compared to the standard DLSIM.
7%. Is that a big deal in this context?
It is significant, yes. It means the reconstructed image is mathematically closer to the true structure with fewer deviations caused by artifacts. It points to higher fidelity, more trustworthy results.
So for biologists using SIM, this could mean more reliable data, broader application.
That's the hope. making high-resolution imaging more robust, especially when conditions aren't perfectly ideal, which, let's be honest, they rarely are in complex biological experiments.
It really highlights how crucial it is to think about the data deep learning models see, not just the model architecture.
Absolutely. Domain knowledge and understanding the physics of the data generation process are key.
Now, maybe we should step back for a second, put this in a bit more historical context. Like, why did we even need things like SIM in the first place?
Good idea.
Yeah.
Yeah, it all goes back to the fundamental limits of light microscopy. For centuries, microscopes were limited by diffraction.
The Abbe diffraction limit, right. Light waves just sort of spread out, blurring tiny details.
Exactly. Ernst Abbe figured this out in the 19th century. It meant you couldn't really resolve things much smaller than about 200 nanometers using visible light, a hard wall.
Which is frustrating if you want to see the really intricate machinery inside cells.
Totally. But then, starting around the late 90s, early 2000s, this wave of innovation happened, super resolution microscopy.
It's Storm, Palm, Stead, those Nobel Prize winning techniques.
Those are the big ones, yeah. Each found a clever way, often using fluorescence, to sidestep the diffraction limit and see things at the nanoscale. It absolutely revolutionized cell biology.
So where did SIM fit into that picture?
SIM came along as, let's say, a more accessible, maybe gentler approach for certain applications. It didn't always reach the absolute highest resolutions of Storm or Palm, but it offered maybe double the resolution of a standard microscope.
Which is still a big jump.
A very big jump, yeah. And crucially, it was generally faster and often more compatible with standard fluorescent labels biologists were already using. Plus, less harsh light on the cells.
Making it good for watching things happen live.
Exactly. Live cell imaging became a major application area for SIM. You could see dynamics you just couldn't resolve before.
But, as we discussed, the early versions had their issues. The reconstruction was tricky.
Very tricky. You needed really precise calibration of those light patterns, and the algorithms to unscramble the raw data were complex and sensitive. Small errors could lead straight to those artifacts we talked about.
Which limited how widely people could reliably use it, I guess.
It did. It required a fair bit of expertise to get right consistently.
And that's where the idea of applying deep learning started to gain traction as a way to maybe handle that complexity better.
Precisely. The thought was, maybe a neural network could just learn the complex mapping from the slightly messy raw data to a clean, super-resolved image without needing perfect calibration or explicit physical models for every imperfection.
Let the data do the talking, essentially.
Sort of, yeah. And the initial DLSIM results were promising. Networks like UNets showed they could produce good-looking reconstructions, sometimes faster, sometimes with fewer apparent artifacts than traditional methods. People developed models needing fewer raw images, which is great for reducing light exposure.
But then came the realization about the out-of-distribution problem. The models worked well until they didn't.
Right, that generalization issue. Great results on data similar to the training set, but less reliable when faced with different samples, different microscope quirks, different light field distortions.
Which brings us right back to LSIM and its awareness approach, trying to make the model robust to those real-world variations by explicitly estimating them.
Exactly. It's an evolution acknowledging that supervised learning alone, trained on potentially idealized data, isn't always enough for messy, real-world science.
Okay, let's dig a bit deeper into LSIM itself. You mentioned the two stages. Can we walk through that pipeline again, maybe thinking about the networks involved?
Sure. So, stage one, light field prediction. They use a neural network, specifically a UNet architecture, which is pretty common in image-to-image tasks.
UNets are good at capturing spatial information at different scales, right?
Yeah, they have this encoder-decoder structure with skip connections. So the input is the raw SIM data, typically 9 images for 2D SIM, corresponding to different illumination patterns.
Okay.
This first UNet actually has 2 output branches, 2 decoders. One predicts the light fields.
The potentially distorted ones.
Yep. And the other decoder simultaneously predicts the underlying structure, the emitters, like the fluorescent molecules.
Why predict the emitters too in this first stage?
It seems to help regularize the training, guide the network. The main goal here is the light field prediction. But predicting the emitters too provides an additional constraint. The loss function compares both predictions to their ground truths during training.
Got it. So stage one trains this network to get good at predicting both light fields and emitters from simulated known data.
Correct. And the crucial output from this stage is the predicted light fields.
Okay, so now we have estimated light fields that should reflect reality better. What happens in stage two?
Stage 2 is training the actual reconstruction network. This is another UNet, similar architecture, but its job is just to take raw SIM data as input and output the final super resolution image, the emitter distribution.
Right.
But how it's trained is key. Remember those light fields predicted by the first network?
Yeah.
They use those predicted light fields, maybe from real experimental data passed through the stage 1 network, to generate new simulated raw SIM images.
Yeah.
They combine these realistic light fields with simulated emitter patterns, add noise, background, simulate the optics.
So they're creating synthetic training data that incorporates the kind of light field weirdness the first network detected.
Precisely. This data set is then used to train the second UNet. The loss function here just focuses on how well this second network predicts the emitters compared to the ground truth emitters used in the simulation.
So the final model is trained to reconstruct images even when the illumination isn't perfect, because its training data reflected those imperfections.
That's the core idea. Train on data that looks like the real thing, including its flaws.
And the data synthesis itself sounds quite sophisticated. They didn't just use simple patterns.
No, they used a mix for the emitters, random points, curves, even structures derived from natural image data sets like COSHO to make it more realistic. And for the light fields, they started with ideal cosine patterns, but then deliberately added various simulated distortions and aberrations.
And noise, background, the microscope's blur function.
Yep, the point spread function, PSF, Gaussian noise, background signals, trying to mimic the whole imaging process computationally.
What about the loss function? Anything special there? You mentioned it compares predictions to ground truth.
Yeah, they used a composite loss. It combines two metrics. One is the multi-scale structural similarity index, MSSSM.
Which is good for perceptual similarity, right? How images look similar.
Exactly. And the other is the standard L1 loss, which measures the absolute pixel-wise difference, good for pixel accuracy. They combine these weighted for both the emitter prediction and the light field prediction in stage 1.
So balancing looking right with being numerically right.
Pretty much. It's a common strategy in image restoration tasks.
And they actually built a microscope and tested this on real cells too, not just simulations.
They did. They described their setup a double beam interference sim system using a spatial light modulator to create the patterns, lasers, cameras, the works. And they imaged fixed BSC1 cells labeled with an actin stain.
Standard cell biology stuff. And they compared AlSim to
conventional SIM using a standard algorithm, FairSim, and also to a standard DLSIM network, basically, just the second stage UNet from AlSim, but trained on idealized simulated data without the light field awareness part.
Okay, so that gives a direct comparison for the benefit of the awareness component.
Exactly. It isolates the effect of that first stage and the improved training data.
Right. Let's talk results then. What did they see first in the simulations?
Okay, so in simulations, they could really control things. They created a training set with certain types of light field distortions and then a test set with different distortions. This specifically tests generalization.
The out of distribution scenario again?
Precisely. And visually, the standard DLSIM, trained on the first distortion type, showed significant artifacts when tested on the second type. LSIM, however,
handled it better?
Much better. The paper has figures showing the distorted fields, the raw images, and the reconstructions. LSIM's results were clearly cleaner, fewer spurious patterns. And quantitatively, that's where the NRMSE numbers came in, LSIM lower than DLSIM.
Okay, so it showed robustness to unseen distortions in simulation. What about the real-world SIL data?
That's often the tougher test.
Yeah.
They showed images from conventional SIM first. It improved resolution over standard wide field microscopy, as expected, but
artifacts.
Yeah, particularly near bright spots, you could see those characteristic SIM artifacts creeping in.
Right.
Things like residual pattern noise or doubling effects.
And the standard DL-SIM trained on ideal data.
It also showed artifacts because, again, the real light fields in their microscope inevitably had some distortions not present in its idealized training set. That training test mismatch kicked in.
And LSIM.
LSIM's results looked substantially cleaner. They highlighted specific regions, sparse areas, dense areas, and in both, LSIM showed fewer artifacts than both conventional SIM and the standard DL-SIM. The side lobes around bright structures were much reduced.
Did they look at this in frequency space too, like Fourier analysis?
They did. The Fourier transforms of the images are revealing in SIM. Artifacts often show up as specific unwanted frequency components. LSIM's Fourier spectrum looked cleaner, with those artifact components suppressed compared to the others.
Interesting. What about resolution? Did LSIM compromise resolution to reduce artifacts?
That's a key question. They measured resolution using a couple of methods. One standard method, FWHM, on small features showed wide field around 340 millimeter, conventional SIM maybe 250 millimeter.
So better than wide field, but not quite the theoretical 2x improvement.
Right. DL-SIM and Al-SIM were both much better, down around 170 millimeter by that metric. Very similar.
Okay, so roughly similar resolution boost for both DL approaches there.
But then they used another method, decorrelation analysis, which can sometimes be more robust, especially if artifacts are present.
And
Here the results were more striking. Wide field was around 270 millimeters. Conventional SIM actually looked worse than wide field, likely because the artifacts were interfering with the measurement.
whoa.
DL-SIM came in around 160 millimeter, similar to the other method, but Al-SIM, it measured significantly better, down around 84 nanometers.
84 nanometers, that's a huge jump, more than double the diffraction limit. Why the big difference between the methods?
Their interpretation is that the decorrelation method is sensitive to artifacts. Because Al-SIM removed artifacts so effectively, the analysis could reveal the true underlying resolution more accurately, which was masked by artifacts in the other methods.
So cleaner images might enable more accurate resolution assessment, potentially revealing even better performance.
Plausibly, yes. It suggests the potential resolution was there in DL-SIM too, but hidden by the artifacts Al-SIM removed.
Okay, so summing up the results. ALSIM demonstrably reduces artifacts in both simulation and real data, leading to cleaner images and potentially allowing for more accurate resolution measurements that show a significant improvement.
That's a fair summary, yeah. The core idea is that by improving the consistency between the training data and the actual experimental data via light field estimation, it tackles that out-of-distribution problem head-on.
Makes sense. Did they discuss limitations or future work?
They did. They acknowledged that estimating the light field might be difficult in really challenging conditions, very low signal-to-noise, very sparse molecules, or low contrast images. The network needs some information in the raw data to infer the field from.
If there's barely any signal, it's hard to tell what the illumination was doing.
Right, and they suggested future work could involve trying to compensate for the light field, even in regions where the estimation might fail, maybe interpolating or using priors. They also mentioned the potential applicability beyond the simple cosine illumination patterns used in standard SIM.
So the core message is, this awareness principle significantly improves DL-SIM robustness and reduces artifacts by correcting for real-world illumination issues.
Yes, leading to more reliable super-resolution imaging, especially in complex or non-ideal scenarios.
Which has some pretty clear real-world implications.
Absolutely. I mean, first off, it potentially makes SIM a more reliable tool for a wider range of biological samples and experimental setups. Places where getting perfect illumination is just hard.
Like imaging deeper into tissues, maybe? Or using different kinds of samples that scatter light more?
Could be, yeah. Anywhere the light field gets messed up. Second, by reducing artifacts, it makes the interpretation of dynamic events in live cells more trustworthy. You're less likely to mistake an artifact for a real biological structure changing.
That's huge for quantitative biology. You need accurate images to measure things reliably.
Definitely. Higher fidelity reconstructions could lead to better measurements of protein clusters, organelle dynamics, all sorts of things.
And thinking bigger picture, this concept of awareness, making the AI model account for the physics or the state of the instrument, seems like it could be applied elsewhere too.
I think so. You can imagine similar ideas in, say, electron microscopy dealing with sample charging, or MRI dealing with field inhomogeneities.
Yeah.
Anywhere the data acquisition process itself has variations that affect the final result.
Yeah.
It's about building more physics-aware or instrument-aware AI.
Very cool. It's moving beyond just pattern recognition towards models that have some understanding of the data's origin.
Exactly. A step towards more robust scientific AI.
Okay. This seems like a perfect transition to our novel notions segment. Where could this idea of light field awareness go next?
Right. So building on this, one idea that comes to mind is active light field adaptation during imaging.
Active adaptation, so not just estimating it after the fact.
Exactly. Imagine the first stage network isn't just run once. What if it continuously analyzes the incoming raw data frame by frame, or maybe every few frames, during a live cell experiment?
Okay, providing a real-time estimate of the light field.
Yeah. And then here's the active part that estimate feeds back to the microscope hardware itself.
Yeah.
Specifically to the spatial light modulator, the SLM, that generates the patterns.
You mean the system could adjust the illumination pattern on the fly to counteract detected distortions?
Precisely. If the network detects, say, a slight drift or a new aberration popping up because the sample moved a bit,
It could tweak the pattern being projected by the SLM to pre-compensate for that distortion.
that's the idea. It creates a closed loop, estimate the distortion, then modify the input illumination to cancel it out,
Right.
or at least reduce its impact on the raw data before it's even fully recorded.
Wow, okay, so you'd be preventing the artifacts from even forming strongly in the raw data in the first place, rather than just correcting them during reconstruction.
Potentially, yes.
Hmm.
It could lead to fundamentally cleaner raw data, which might push the resolution and image quality even higher. It's like giving the microscope adaptive optics, but driven by a learned model of the illumination.
That could be revolutionary for long time-lapse imaging, where things inevitably drift or change. A self-correcting microscope.
It's ambitious, would require fast computation and hardware control, but the concept is powerful. Self-calibrating systems.
Okay, that's one fascinating direction. What else?
Another angle is integrating physics-based priors into the light field estimation network.
Bringing more physics into the AI.
Right. Currently, that first stage network learns the light field distortions purely from the data it sees during training, which works, as the paper shows. But
Well, we actually know a lot about optics, right? How light behaves.
we do. We have mathematical models for light propagation, scattering, common aberrations in microscope objectives. Why not bake some of that knowledge into the network?
How would you do that? Change the network architecture or the loss function?
Both are possible. You could design network layers that explicitly model certain optical transformations. Or you could add terms to the loss function that penalize light field predictions that violate known physical laws. Think physics-informed neural networks, PINNs, but applied to light field estimation.
So you're guiding the network's learning process with established physics.
Yeah. Instead of it having to discover, say, the mathematical form of spherical aberration entirely from scratch through examples, you give it a hint, a prior based on optical theory.
What would be the benefit?
It could make the estimation more accurate, especially when data is limited or noisy. It might generalize better to completely unseen types of distortions if they still follow physical principles. And potentially it could reduce the sheer amount of training data needed, because the network isn't starting from a blank slate. It has some physical intuition built in.
Especially useful for really tough conditions like deep tissue where scattering models are complex but somewhat known.
Exactly. Combining the power of data-driven learning with the robustness of physical models, that's a really active area in scientific ML right now.
Both of those sound like really promising avenues stemming from this core idea of light field awareness, active correction, and physics-informed estimation.
Yeah, it opens up quite a few possibilities.
So to wrap things up, ALSIM really feels like a significant step in making deep learning for super-resolution microscopy more practical and reliable.
I'd agree. By tackling that out-of-distribution problem head-on, by making the system aware of the actual illumination conditions, it offers a path to reduced artifacts and more trustworthy results.
The benefits being clearer images, potentially better effective resolution once artifacts are removed, and broader applicability for SIM across different, maybe challenging biological studies.
Definitely. We certainly encourage listeners interested in the nitty-gritty, the network details, the data synthesis, the full experimental validation to check out the original paper.
And maybe a final thought to leave our listeners with. How else could this principle of awareness, of making our analytical tools cognizant of the context or the physics of data generation, be applied in science?
It's a great question. Moving beyond black box models to systems that integrate domain knowledge seems crucial for building truly robust and interpretable scientific AI.
Food for thought indeed. Well, thank you for joining us on this deep dive into ALSIM and the cutting edge of machine learning and microscopy.
My pleasure. Always fascinating to see how these fields intersect.
Until our next exploration, keep those neural networks firing.